Given the huge success in large language model powered by like powerful computation, a large amount of data, and transformer-based architecture, this success has expanded naturally towards the robotics. And for the past like 4 to 5 years, given this vibe, many players in robotics field have made like tremendous achievement in RFM. So I'm showing you several examples of those like players on this slide. You guys may have heard like Dyna, Pi, journalists. There's a typo, I'm sorry about that. But these players are generally pursuing like what's the models so-called VLA models. The previous presenters have explained about VLA, so I'm not going to go into details about this. But there's another like stream of players who are pursuing slightly different approach where people, try to use the model, so-called world model. Different companies are pursuing slightly different like approach at various angles, but all in all, like the commonality is that they're all pursuing data-driven approach. This data-driven approach has been showing great promise, as you can see from these examples. But most players in the field are focusing on one task at a time. Like this is a pretty good approach to make a decently working vertical model. Like basically like a Dyna. They're very highly specialized in tall folding. They're doing great. But actually, if you look into the model's performance very carefully, making perfectly working one vertical model is even very difficult because you often see that these models are fragile under unseen conditions, basically conditions that's not covered in the training data the model was provided. Then like you can imagine how even more difficult it would be to make a general purpose RFM, right? And Config Intelligence, our goal is to work towards making the general purpose RFM. And then we have to answer the questions why this is a problem and what is important to like tackle this problem in an efficient way. As previous presenters have already covered so many times in a really nice way, you guys already know that the problem is the data. More specifically, scaling data for robot learning has been very difficult. Then we have to ask questions, why is it hard, right? For this question, we think the answer is the following. So as you guys are familiar with, large quantity is always the top priority. But it's not the quantity that matters the most, actually. So to achieve the generalizability of the model, you need to contain like good amount of diversity into the quantity while maintain the good visual clarity and the task-focused action information into that. So we call that like high-quality data. And it sounds like, yeah, pretty obvious, right? But let me try to visualize this to help us like what I really mean by this. So I think RFM is, we can just think it as a function which takes the data, which can be a set of like language instruction and visual information about the environment and object that the robot needs to interact with. And given that, it's a function that outputs the relevant action that robot needs to make, right? So the training data that we're talking about is a set of different pairs of instruction, environment, object information, and the relevant action given to all of that. So how do we need to scale this? So in principle, this data lives in a high dimensional space. So I call action as just one word action, but in reality, this is a combination of many different types of physical quantity. So this itself is already high dimensional. But just for the sake of like this talk, I want to keep it simple. So let's just think it as like we are in the three-dimensional space for the data. So where the each axis is basically action, environment, and object. And within this 3D space, if we make a data set for one vertical task, this can be represented as a blob or volume in this 3D space. And this blob is basically for one or like a set of language instruction. So when I mentioned about the models that specialize in one vertical task, it's going to be about like establishing one big blob within this 3D space, which is humongous, by the way. And by establishing this one blob, like you're likely to build like decently performing the model for one specific task, but for the conditions that's well covered within this blob or seen conditions. So I'm giving you an example where you can imagine different types of data blobs specialized in verticals. Like for instance, recycle sorting, vegetable chopping, dishwashing, which all seem to be kind of irrelevant, but if you think about it carefully, they kind of share some commonalities in different directions. Like maybe like chopping, sorting, they have some similarity in the action space whereas they are interacting with different type of objects. So the key to go to the generalization of the motor capability, we claim that it is extremely important to quickly increase the coverage of the data within this 3D-dimensional space. So for instance, not only 3, but establishing the data set for different verticals like with many more numbers, right? Why is it important? So we believe that this is like the pathway towards the emergent generalization of the model capability. So, and here what I mean by the generalization, I think we can interpret that in like 2 different ways. First of all, as an effective union of those like independent blobs, you can literally expand the coverage of the data set, and thus model get to learn different context that's well contained within each blob. I think that's pretty clear, right? But there's a secondary effect, which is called a composition effect, I call. So I think it's going to be practically very difficult to increase the coverage within this data parameter space uniformly across the entire area. So likely you're going to have some holes here and there, like for instance here, right? But we know the model is pretty good at learning through interpolation to like the unseen correlation between these 2 blobs in the latent space. So we believe that that's another source of the generalization of the model. And in order to efficiently achieve the generalization in this context, we think it's not only important to increase the wide coverage, you need to really keep the density of those blobs or the quality of the data within each blob. So it is not about just making like 10 scenarios of data in like each blob and quickly move on to the next and so on and so forth. You really need to maintain the good quality and the density within each blob while expanding pretty quickly across different verticals, right? So yeah, we keep increasing that. We believe that this emergent coverage area will be growing more, and it sounds so good, right? Data scaling is just great. Nothing bad about this except the money, I think. But as I've been emphasizing, and also other presenters have been doing, it is very difficult. And let me explain why that's the case. So first of all, the main method that most players in the field have been pursuing is called teleoperation or 원격 조정. So to do this, we need like several factors. First, you need a robot. And robot, as you guys know, is damn expensive. Like 수천만 원, 1억, whatever, right? And it is not only expensive, it is highly maintenance dependent. What I mean by that is, robots is made out of like gears and actuators and like wires, whatever, all the hardware components, but they're not perpetually living. So as you keep using it, they degrade, so you need to ship them back to the factory to like repair them. It takes time, it's another cost. Not only the robot, but also you need like peripheral devices, which are often not that cheap, like VR devices, like a master arm slave, like the ones you can see in these examples. And another factor is human, right? You want to have a human to operate the robot, but it is not just ordinary human. Like you'll be surprised if you don't have any experience in this field, you'll be surprised that it is how difficult it is to train highly skilled person like adequate for this job. It is not like a just normal toy usually. So you need a lot of training period to make really great quality teleoperation data. So it's all cost, it takes time. So, okay, quality of teleoperation is great, we all know that, but I'm just saying that it is not so trivial to scale the data only with this method. There's a second bottleneck. So I've been emphasizing diversity, right? Diversity of the data. So preparing for the diverse yet task-specific data scenario is also not so trivial. So let's think about the desk organization task. So you can think of millions of different type of objects you can think of when it comes to your own desk. MacBook, like whatever, like scissors, pens, staplers, so on and so forth. And if you consider different combinations, permutations, all of different objects, it's gonna be a huge number. How are we gonna teach the robot to understand all different contexts, right? It's gonna be very chaotic. So you need to really think about how to build a system to tackle this problem when it comes to providing the data collectors to, collect the data, like for this humongous number of different data scenarios. And then within each data scenario, you really need to detailedly describe what the goal of the task and what's the object you're interacting with, in which type of environment, and how those objects are configured as an initial configuration to start with. So it sounds all obvious, but if you think about when it comes to systemizing this is actually not so trivial. So we Config Intelligence are trying to solve this, basically resolve this bottleneck with mainly two components. First is called automated systems for designing the data scenarios. Second is a low-cost data acquisition pipeline, mainly powered by human, not by robots. With this two, we have built fast and low-cost end-to-end pipeline, which start from the designing the data strategy, all the way down to training the model and then evaluating its performance. So far with this pipeline, we can make a one task specific model within about 2 weeks with the cost of $2,000. So let me go into each component in a more detailed way to help you understand what I mean by that. So first of all, how we design the data strategy, right? So I already explained to you about it is not so trivial to make diverse and very task-specific scenarios. So main component within the heart of data design system at Config Intelligence is through LLMs. So I think you guys are a big fan of LLMs like ChatGPT and stuff. We all use that. So we give LLMs with task description, which can sometimes be as high as the office organization, sometimes as low as folding towels or making ramens. So as an input, given this input, LLMs are trained. Basically, we prompt engineered for it to produce diverse yet detailed and also executable scenarios. But we all know that LLMs are not perfect, so we need something else. So when it comes to the objects that LLM needs to think about, we want it to be more realistic. So we have built a database for the objects that we have in-house, where we have organized the metadata information, for instance, size, color, and deformability of the object that we have. So given all that information, we made the LLMs to produce really executable scenarios. So output will contain high-level test goal, basically what data collection needs to achieve given the data scenario, and also step-by-step low-level strategies that data collector needs to follow, and also the types and numbers of the required objects and how they need to configure as an initial condition. But again, we know that LLMs are not perfect, so we have a human in the loop. So validator is validating the output of the LLMs to really increase the purity of the data scenarios. So all this process has been automated in-house. And here I'm sharing you with a photo of one of the aisles of the warehouse that we have in-house. So we are kind of like small coupon, so to speak. I'm just kidding. But we basically store many different type of objects that we think is valuable within our data set. And as I said, we are at the same time building the database for the meta information of those objects here. And just for the flavor, just for your flavor, when it comes to office organization tasks, we have built about 500 different scenarios with 55 different type of objects. This is sort of outdated, actually. So we are actually making more numbers of scenarios and objects as of now for the office organization task. And this is example output. So as I said, we are detailing how the required object needs to be configured, what task needs to be achieved at the end of the day as a high goal, and what steps of the data collector needs to follow step by step to really specific about the steps that it need to follow to provide a model to learn how to achieve the goal from the beginning to the end in a very systematic and organized way, so to speak. All right, so we made a data scenario. We are ready to acquire the data. And then I promised you that we lowered the cost a lot when it comes to acquiring data, mainly using the human resource, right? So we have built Data Studio, Config Intelligence Data Studio. We call it DS. And then we have a human-based DS mainly at Vienna, Hanoi. There we have a bunch of people holding handheld gripper, which is basically resembling the end effector that we're using for the robot that we're targeting as of now. And then they're producing about 20K hours of data per month. And again, like their labor cost is so much cheaper. Infra costs, we made it like so much cheap. So it just compared to teleoperation data, the per money throughput of the data is like about more than factor 10 higher. And then from this facility, we're making 10 different tasks, about 100 different tasks per month. And for some reason, we also need some like quantity of the teleoperation data, and that we have some bimanual robotics set up in Seoul. There we make about 500 hours of teleoperation data per month. So this is a snapshot of how we have been accumulating our data with this DS facilities. So as of now, the total cumulative hours of the data is about more than actually 1 million hours. I think like it was very close to 2 million almost when I stepped out of the office today. So this is substantial. And just to give you a flavor how this data look like, this is the like some snapshot that I have like made it as GIFs. So since we matched the end effector to reduce the visual disparity between human and robot, as you can see, they look kind of similar, right? But you might get questioned like, is it really similar? But let me get back to the point later. All right, so we got the data, but we really need to make sure if this data are really useful to train the model in a smart way. So if you think about the teleoperation, why is it high quality? Because it naturally contains the extra information within it, right? But human data, they're not robots, right? We're not outputting any we are producing electrical signal through the muscles, but we're not recording it. So how are we gonna actually make them useful in a like action labeled way? So we need to find a way to label the action to the human data and then use that to train the model. So let me explain how we do that. So to label the action to this human data, we develop a model so-called inverse dynamics model. So this model is basically trained with a small set of teleoperation data. So given the visual information, it learns to output or label the action given the visual information. So when we use this trained model to label the action for the human data, basically it labels the action for us. So that's where the decreasing the visual disparity between human and robots is very important. Otherwise, this model is not going to be effective, right? So to achieve that huge reduction in visual disparity, we use various techniques, including embodiment removal, adversarial learning, and so on and so forth. So I think like this talk, like going into the deep about this topic is out of the scope for this talk. So I'm not going to touch on that. But if you're curious, I'm happy to talk about this after this talk. So please let me know. So we label the data on the human data, and then we use that to train the policy model. And sure, yeah, we have a trained model, but we want to know how well it's performing, right? So the best way to confirm the quality of the data that you produce is to measure the performance of the model that you trained the data with, right? So we need to also have the like proper evaluation pipeline for our model. So this is roughly how we evaluate our model's performance. So we have a very systemized way to measure the performance. So just to make a fair comparison between of the performance among different models, we have a preset of the evaluation scenario, like you see here on this photo, and that we basically measure task progress score based on the evaluation rubrics you see in the red box. So this is basically the score that you get, or the model gets, based on how far you go from the beginning all the way to the end goal. So we measured that for 5 different rollouts, and then we actually also let 5 different people or laborers to basically label the score for that. And then in that way, we can make a proper, more statistically more stable like model performance in that way. And here's one of the examples out of that evaluation pipeline. So for the task organization, on the left side, or the hollow bar, this is basically the model that's like fine-tuned only with the teleoperation data on the backbone that grew N1.5. And the purple is basically we pre-train it, the backbone, with the human data, and then fine-tune it with the teleoperation data. As you can see, purple outperforms kind of like okay level at the seen conditions, but the main boost comes really from the unseen conditions. So I want to say that unseen condition contain both only seen in human data and also completely unseen in both teleoperation and human data. So this really talks about the generalizability of the model capability that I've been talking about. So as you can see in this case, more than 30% boost has been achieved only by training the model, the backbone, with the human data as a pre-training step, which was not being able to achieve only with the teleoperation data fine-tuning step. And here's an example video of to show you how this model is performing. So in this case, the instruction was to put the can into the trash bin and close the lid. This is a seen task, by the way. And one thing to pay attention to here is that it tries to close the lid, but it keeps failing for some reason. But it doesn't stop. It keeps trying until it makes success. So it shows the a robustness against the failure. And what about for unseen case? So on the left, the task is to put the red can into the trash bin, and then it has not seen the red Coke can in the context of office organization domain, both in teleoperation and human data. It may have seen it and learned it from different set of data that's not within the office organization task. It may have been not about picking it up and putting it into the trash bin, but it understands it through the learning latent space. Right. On the right hand side, it has never seen so many staplers scattered on top of the desk like that, but it understands what to do. Another example, this is task we call candy serving. The task is to scoop candies into the cup and then basically serve it on the tray. As you can see, this is a scene scenario, by the way. As you can see, it successfully, repetitively, completes the task. A person keeps, a person that's not shown in this video, keeps clearing out the filled cup and then putting a new cup on the various positions of the tray, and then it recognizes it and then keeps completing the task, right? It's pretty robust. But what about for unseen task? On the left, this is a scenario where we replace the color of the bowl and the cup, and also content of the bowl to the black beans. So this is only seen in human data. As you can see, what's learned from the human data is well captured. And on the right-hand side, again, this is completely new. The model has not seen it in either teleoperation and human data. But it successfully recognized the candy given the instruction. And then I have to acknowledge it was kind of wobbly at the end, but it really tries to complete the task with the success. Just to give you more flavor, we have experimented with different type of objects. And one of them is the deformable objects, like a cloth. So this is not hard, well-structured object, and thus how it needs to approach and how, in which angle the gripper approach, it changes everything about the object in terms of shape. So it's very delicate. But as you can see, it's doing pretty well when it comes to folding the polo on the desk. On the right-hand side, this is trickier because it grabs the towel out and then put it onto the table. Then the shape of the towel is just very chaotic. Every time it puts out the towel and put it in, it's not guaranteed that it's going to be in the same shape that you see in the training step, right? But it learns to, just kind of flatten out until it thinks it's that ready for its right manipulation. And also, it's pretty robust to human intervention. So in this case, the instruction was to put the crumbled paper into the trash bin. It tries to do that, but human was pushing of the trash bin, but it recognized well. And it was trying to grab the paper, but it was pushed to a different location. They step back and tries to find its location again, and then continues over. All right, so I kind of rushed through at the last minute, but hope I gave you entertaining and educative context from our work that we've been doing. So let me conclude this talk with the vision that we have. So as I've been emphasizing, our vision is to quickly expand our task library, and by doing so, we want to efficiently achieve the model's emergent coverage, expand fast, and we think that's the right way to. Or there can be any other right approaches, but we think that this is one of the right approaches to achieve the general purpose RFM. And we also plan to increase the data and the model coverage for diverse types of robots and effector next year. And we plan to release our models. We plan to open source our models and data set before the end of this year, along with the technical report. So if you're interested in, please stay tuned. Thank you so much.